You press a key, and within tens of milliseconds, a list of search suggestions appears. But behind that split-second response lies a massive logistical challenge. To generate those specific suggestions, the system has to continuously ingest, aggregate, and rank millions of global search inputs. You cannot calculate these rankings dynamically. Scanning billions of historical search records the exact moment a user presses a key is computationally impossible. Attempting real-time aggregation on the read path forces the CPU to calculate rankings across billions of records while the user is still typing. This creates immediate memory pressure and erratic latency spikes that break the user experience. The solution requires strict structural isolation. We have to separate the act of reading data from the act of calculating it. To achieve sub-millisecond response times at global scale, the architecture must be split into two entirely isolated pipelines, one engineered purely for reading and one engineered purely for writing. This diagram illustrates that split. On the left is the request flow. It is a highly streamlined, linear path from the user's client, passing through a load balancer and going straight into a memory cache. This side is completely latency-bound, built to serve pre-computed answers instantly. On the right side is the data collection flow. This is a complex, multi-layered pipeline built to handle intake streams, hashing bounds, and heavy database clusters. This side is throughput-bound. It handles the heavy lifting, batch processing raw logs, and running the mathematical ranking models in the background. These two pipelines do not wait for one another. They operate entirely asynchronously. By decoupling the read and write paths, engineers gain the ability to scale them independently. We can dedicate rapid access memory for instant user feedback, while provisioning heavy disk storage for long-term data analysis. To understand the read path, we start with the foundational data structure for string search, a trie. This tree maps characters to nodes, allowing a system to trace prefixes like bat, ball, or bit. A standard trie fails under massive load. If a user types the letter B, the system has to traverse every single sub-branch connected to B, gather every possible match, and rank them all on the fly. To bypass this deep traversal, we have to pre-compute the highest-ranked terms and store them where they are immediately accessible. This is a top K trie. Every single node contains an embedded array of the top completed terms and their weights. When a user types B, the query extracts this pre-computed array and returns them instantly. It never travels down to A or I. This pre-computation replaces an expensive O of n subtree traversal with a constant O1 read operation. Caching answers directly inside every node means the database does zero analytical work during a live user query. The heavy lifting is already finished before the user even touches the keyboard. A trie containing billions of weighted English phrases requires vast amounts of RAM. It physically cannot fit into the memory of a single machine. We solve this by horizontally sharding the data. The massive single trie fractures into smaller, separate tries, distributed across distinct server nodes. We split the data by prefix ranges. Searches from A through K go to one cluster, L per Z to another. To direct traffic, a coordination service like Zookeeper maintains a strict routing table, mapping these alphabetical ranges directly to the correct server IP addresses. To ensure high availability and prevent catastrophic data loss, each shard is fully replicated across multiple secondary nodes. As the global dataset grows, we simply add more shards and update Zookeeper. The routing remains exact, and read latency stays flat. But this introduces the critical question: where do the numeric weights cached inside that top K trie actually come from? Every time someone completes a search on the front end, the system generates an event log containing the chosen phrase and an initial weight. Pushing these millions of raw, individual log entries directly into a storage database would trigger extreme input-output operations per second. The sheer volume of concurrent writes would crash the database. We defend the database by placing a hashing and aggregation layer in front of it. A continuous stream of individual search terms hits a hashing function, routing identical phrases, like thousands of people searching for bat, into dedicated aggregator buckets. These aggregators hold the queries in memory for a set interval, perhaps 5 minutes. They tally the total counts internally, and then execute a single, highly compressed batch write to the database. This intermediate step absorbs the massive throughput spikes, reducing database write operations by orders of magnitude and making global data ingestion sustainable. Once aggregated, the data is stored in a NoSQL database, like Cassandra, which is heavily optimized for high-volume write throughput. We have to track this data chronologically. Search trends are volatile. A system must distinguish between what is trending right now and what was popular a month ago. This NoSQL schema maps each phrase to a time series. The columns are broken down by hourly granularity, with older data eventually compacted into daily columns, summing the total weights. Compaction saves storage space. As data ages, hourly records are rolled up into daily records, and eventually the oldest data is dropped entirely. This temporal structure allows the system to apply a recency bias. During final ranking calculations, recent hourly data is mathematically multiplied by a higher weight than older daily data. Because we store data with strict temporal granularity, the algorithm can instantly surface breaking news and viral spikes, pushing them above historically popular but stale queries. We now have a massive NoSQL database full of accurately ranked, temporally adjusted search terms. We need to get that data into our distributed tries. We bridge that gap using an applier service. The applier pulls the finalized time series data from the database, calculates the definitive top K lists, and pushes the updates out to the Zookeeper-managed try nodes. This process runs continuously in the background on a pre-configured schedule, updating the system every 10 or 15 minutes. Crucially, the applier builds a miniature, updated version of a specific try range in its own local memory first. Once complete, it atomically swaps the new try into the live cluster without interrupting service. The applier is the final piece of the structural isolation. It fully insulates the live, latency-sensitive search servers from the crushing weight of the database read and write cycles. Even with a perfectly optimized backend architecture, the physical distance between the user and the primary data center can still cause network latency. We mitigate geographic distance by deploying content delivery networks, or CDNs. The absolute most popular prefixes are cached on CDN nodes physically located in the user's specific city. For these high-volume queries, the request never even reaches the main backend. Client-side prefetching targets the remaining network delay. When a user types B, the server replies with the results for B, but it also bundles the results for BA, BE, and B in the exact same payload. By sending the highest probability next keystrokes in advance, the client machine can populate the drop-down menu instantly from its own local memory on the very next keystroke. The fastest network request is the one that never has to be made. Looking at the entire system architecture, the contrast is clear. The request flow handles a rapid, extremely lightweight path on top, while the data collection flow executes massive, continuous loops underneath. Autocomplete performance depends less on raw algorithm speed and more on how a system isolates its data logistics. At massive scale, achieving extreme low latency and high availability requires one core architectural principle. You must completely shift the computational cost of processing data off of the read path and onto the write path.